Hi all, welcome to the NPTEL online course Biophotonics online TF program. I am Jijit, your teaching assistant of the NPTEL online certification course Biophotonics. I am a research scholar, an interdisciplinary research scholar of IIT Madras, and I'll be going through some of the concepts which is already covered in lecture series, so it can be more useful as well as more understand. Let us wait for some person to join and let's start our understanding. Okay. Let us start our class by starting with the concept of refraction, total internal reflection, optical fibers. Then let us think more about our last seventh week's lectures, which is regarding biosensors and this optical fiber based sensors and metamaterial based sensors and other things. Okay, so sharing my screen such that you can see the diagrams which I am drawing. So I'm sharing my screen. I hope people can see that. Now, let's move to the questions after that. Basic concepts are cleared. So, okay. We'll start with the idea of diffraction. Okay, what is mean by refraction? The refraction is a phenomenon which is happening at the interface of the two medium when light is passing from one medium to another. Okay, we know that in normal ways, light in the corpuscular theory of light, we can consider light as a stream of photons or something. So, normal case, light will travel only in straight line, and this is like one ray, which is actually representing it's a one ray of light, but actually light will be like more than rays, lot of rays combined together, and we can call it as a beam of light. If it's a ray of light or a beam of light, usually if it is coming from a particular source, it will travel in a straight line. Consider this, it's like a source is emitting light in the particular direction, so it will travel like a straight line. So this beam of light, if the beam is very narrow, we can actually represent the light in the form of a ray. So this is called a ray of light. This is in the bracket case, it is a very narrow beam of light. Now we know that the light will travel in a straight line. So if the medium, or actually light does not require any medium for traveling. So lights are actually electromagnetic waves. So that does not require any medium for traveling. But yeah, when the medium is coming, what will happen? The velocity of light will get decreased and its wavelength will also get affected. Something like this thing will happen. And but in a uniform medium or in an extended medium, light will always travel in a straight line. Okay. Now you can see that light. So if there is only one medium, so this is a single medium, and somehow light is traveling, so it will travel in a straight line. Now, what happens if the light is traveling from one medium to another medium? Let us see that when light is traveling from one medium to another medium. So what will be the, so there will be one medium, there will be another medium. So the boundary, so there will be medium 1, there will be medium 2. So the boundary between two medium, we can call it as an interface, because there actually what happens at one point, there will be a particular medium, in the just to the next moment there will be another medium. So there will be, when light is traveling from one medium to another medium at the interface, what happens, actually there is a property, because light is a electromagnetic waves, and this is traveling in the form of the variation in electric field and magnetic field. So as it is passes through a medium, what happens, it is actually changing the property of the medium also. It's actually interacting with the medium and it's getting traveled. So when one medium to another medium there is happened, there will be some change in, due to the change in the property of the medium, there is a change in the light also happens. So what happens when light is traveling from one medium to another medium? Just see that there are different conditions. So that first condition is like that, when light is traveling normally. What is mean by this normal incidence? Normal means whenever we are talking about a particular interface, we will always think about the normal to the interface. That is the perpendicular degree from the interface. So if light is actually traveling to the normal to the interface, that is called a normal incidence. The normal incidence, what happens? There will be some interaction between the light and the medium, and some of the light will get transmitted to the second medium, and some of the light get reflected from the second medium. Okay, and what happens? The speed of the light will change from one medium to another medium. If it has a refractive index n1 and if it has a refractive index n2, the speed of the light in the vacuum, the speed of light will be c, which is 3 into 10 raised to 8 meter per second. But when there is a particular medium which is traveling, what happens? The velocity will be equal to c by n. So c by n1 will be the velocity of the light in first medium, and c by n2 will be the c1 will be the velocity of light in the second medium. Okay, this is the case of a normal incidence. Now we see what will happen when light is incidenting with a particular angle of the interface. So what happen when light is getting incident at a particular angle to the interface? This is the interface, and to understand our concept about normal, I think we will draw a normal to the interface, and all the measurement we will take from the normal. And light is actually incidenting at an angle. Yeah, right, the interface. What happened? Some of the light will get reflected, and the relation between incident angle and reflection angle is governed by law of reflection, which says that theta reflection will be equal to theta incident. So incident angle of incidence and angle of reflection will be same. Now, this is in the case of the reflected beam. Now, we want to know what will happen if the ray is getting transmitted. So in the normal case, what happens? The get light is transmitted inside that beam, but the velocity of the light is different in the second medium. So it has a refraction index n1 and it has a refraction index n2. So what happens? There will be change in velocity. So there are two things can happen. So that's first condition. N2 is greater than n1. So this is called moving from rarer medium to denser medium. The refractive index of second medium is bigger than n1. That means velocity of the light in second medium is lower than that of the velocity of light in first medium. So velocity of the light decreases when traveling from one wave to. So velocity of the light is decreases. So in that case, what happens? So it's a light is moving from denser medium to rarer medium. So what happens? Sorry, rarer medium to denser medium. Light decrease. Velocity of the light decreases. So the refracted beam will be bent towards the normal. So the angle between normal and incident ray is called angle of incidence. Angle between normal and refractor angle is called refractor ray is called angle of refraction. So in this case, what happens? Theta I will be greater than theta r. So it is bending towards the normal. Now comes the other condition. What happens? Now the condition is that n2 is less than n. What will happen? The speed of light in medium 1 is less and speed of light in medium 2 is high. Am I audible? You can tell, or you can use your mic, or you can use this. Seems like some problem with the connection. Okay. What happens if the refractive index of n1 is greater than n2, or n2 is less than n1? The velocity of light in medium 1 is higher, sorry, medium 1 is lower, and velocity of light in medium 2 is higher. In that case, what happens? N2 is less than n1, and the refracted ray will bend away from the normal. Okay, here actually we have two relations. One, we have theta I is, sorry, theta I is greater than theta r. Here theta r is greater than theta I. So depends on the what kind of transmission is happening at an angle, we can say, and it depends on the nature of the medium. So we can actually say that it will bend towards the normal, or bend towards the bend away from the normal, or bend towards the normal kind of things. But this is only a qualitative manner. But we want to know the how precisely or how correctly it will bend, and which law is governing that one. The law which governs the refraction is called Snell's law. The law which governs the refraction is called Snell's law. What it will tells, saying that if there is a refraction happen from n1 to n2, there will be one interface, angle of incidence, angle of refraction. theta is angle of incidence, angle of refraction. Then the relation between theta 1 and theta r is connected with the sine theta I, right? Sine theta r and 2 and r. So there is a nice relationship between the sines of the angle of incidence and sine of angle of refraction. And sine theta I divided by sine theta r is actually give the relative refractive index of medium. Relative refractive and refractive second medium with respect to first. Or we can rewrite it as n1 sine theta equal to n1 sine theta is equal to n1 sine theta 1 is equal to n2 sine theta 2, or n1 sine theta I is equal to n2 sine theta r. And this is called Snell's law. Okay, let us do some calculation based on this Snell's law. Take some time to understand. Let's start some calculations. So let us do some calculations regarding Snell's law. So, so I'm saying a beam of light is actually coming from air to glass. The refractive index of air is given as 1, and refractive index of glass is given as 1.5. Okay, so a beam of light is coming from air to glass at an angle of incidence of 60 degree. What will be the angle of refraction? So we know that the it is coming from rarer medium to denser medium, so it will bend towards the north. So now we want to know theta r h. So we have the equation like n1 sine theta 1 is equal to n2 sine theta 2. So your n1 will 1 sine theta 1. Theta 1 is equal to 60 degree into 1.5 sine theta 2. So what will be sine 60 degree? Sine 60 degree will be root 3 by 2. And so sine theta 2 will be root 3 by 2 into 1.5. 3. So theta 2 will be sine theta 2 1 by root 3. Theta 2 equal to sine inverse 1 by root 3. It will be the answer. It will be around 35.3 degree. So like this way, actually, you can calculate different entities. If angle of incidence is given, angle of refraction can be find out. If angle of refraction is given, angle of incidence can be find out. If angle of incidence and angle of refraction is given, what you can find out to the relative refractive index of the two different medium can be find out. Like that, you can find out different things. Okay, so now we will go towards the total internal reflection. So now we are going to move towards the concept of a total internal reflection. So, what is meant by total internal reflection? Total internal reflection happens when light is traveling from denser medium to a rarer medium. Okay, let's see how it happens. So, total internal reflection happens when light travels from denser medium to rarer medium. We know that the normal case of refraction, what happens? The normal case of refraction, what happens when light is traveling from, let it be N1, N2, light is traveling from denser medium to rarer medium. So let it be N2 will be greater than N1. So it will go, it will bend away from the north theta r. What happens if we increase the theta I more? I more, it will again bend much more towards surface. And again, what will happen if it is increased? It will go in such a way that there will not be any refraction because it will just graze the surface of the, or just graze the interface. So the angle of incidence at which the angle of refraction is 90 degree is called the critical angle or theta c. So just see that what will be the relation with the critical angle and refractive index. So we know that sine I by sine R will be N2 by N1. Okay, or now see angle of incidence sine I, angle of incidence is critical angle sine theta c by sine R. Angle of refraction is 90 degree. Then sine R will be sine 90 degree is equal to N2 by N1. What will be sine 90 degree? Sine 90 degree will be 1. So sine theta c to N2 by N1. So theta c will be sine inverse N2 by N1. Just see that if that N2 means the medium from which sine N2, just see that N2 is air. So the refraction is happening from the medium to the air. In that case, what will happen? Then theta c will be sine inverse 1 by n, where n is the medium from which the refraction is happening. So this is actually proper only. You can see that this n, this n is actually in the case of n will be always greater than 1. So 1 by n will be always less than 1, and only the sign value is always oscillating between plus 1 and minus 1. So here you can see that 1 by n will be always less than 1. So sine inverse 1 will be existing and it will have a particular angle which is between 0 to 90 degree. Okay. So this is the condition. Now we know that this is a critical angle condition. What happens if the angle of incidence is increased beyond critical angle? What happens at the critical angle? At the critical angle, light is actually grazing the surface. So what will happen? A little bit we increase the critical angle of incidence beyond critical angle. Then there will not be any refractions happening, and the whole light will reflect back to the initial, will completely reflect back to the initial medium. And this phenomenon is called the total internal reflection, or EIR. When angle of incidence is more than critical angle, this will be critical angle. So angle of incidence is more than critical angle, all light will reflect back to the denser medium itself, and there will not be any loss in that. So that kind of phenomenon is called the total internal reflection. Okay. So this total internal reflection is the basis of our optical fiber communication, and the optical fiber is made based on the phenomenon of total internal reflection. Okay. Let us do our assignment questions. Okay, let us discuss our assignment questions. Optical transduction is achieved using which of the following phenomena? So, what is mean by a transduction as well, or the transducer? So, in order to understand or in order to detect a particular stimuli or a particular physical property, something is needed which will detect a particular physical property, or it will interact with that physical property and convert and change. Some changes will happen such that which we can detect. So that kind of things actually is doing a transducer. So in the case of an optical transducer, your what you call this whatever we are dealing will be always the light, and there will be one incident light beam which is getting detected by the entity which we are measuring. So that can be anything. So what happens, the light beam is interacting with that particular entity, and some of the properties getting changed, and that can be fluorescence, that can be some scattering phenomenon, and that can be some absorption. So if it's a fluorescence, what happens, some light is getting absorbed and it will get excited, and there will be some light, fluorescent signal, which is actually a higher wavelength signal is actually emitted. You can detect that one, and it will give the properties, some of the properties of the measuring entity. It can be some scattering, and what happens in the case of scattering, it will interact with the particles and interact with the vibration levels and other things. So some Raman scattering can also happens, and what it will give the properties of that particle, and it can give absorb light if the entity is having a proper wavelength uh, or the proper energy level such that it can absorb some of the light. The incident intensity of the light will be decreased, and you can check, understand that intensity of the light is decreased and some absorptions happened, and that also gives some properties of the system. So you can see that optical transition achieved using each of the following phenomena. So fluorescence is also correct, Raman scattering is also correct, absorption is also correct. So what happens, since this is correct, this is correct, and this is also correct, so your option would be D, which is all of the above. Okay. If you have any doubt, just think that. So let us move to the second question. Which of the following are important parameter for a biosensor to be used in disease detection? So a sensor. Now we have to see a sensor should detect a particular property. So I have a sample and I have to get it, and the sample will have a different properties. Properties A, properties B, properties C. property D, etc. And what should be there? There should be, in order to detect a disease, there should be something which we are going to target. Let it be that the targeting entity is a property B. So is the targeting entity is a property B, and then what should be, if that's a good sensor, what should it do? It should actually specifically, it should detect B other than A, C, D. If the A, C, D may be something, some common phenomena which is available in all of the cells or something, if along with the property B, if A, C, D also getting detected, that will actually give some false indication. So that should not be happen. So there should be a specific detection of the property B. So if the parameter of the sensor should be very good, it can specifically detect the particular parameter. So specificity is actually one of the important parameter for a biosensor. Now, what happens then actually comes the other thing, such that how much which we can detect that property B. If that amount of property B is very less, still it can detect that parameter, means that your sensor will be very good, because the property B may be indicating some of the diseases, and the very earlier stage, if you can detect that thing, actually it will give the sensing capacity. It's a very good and useful. So the property B specifically it can detect, and if the very small amount of property or the parameter can give a very high signal or something, we can say that sensitivity of the detector is very good. So sensitivity is also important parameter for a biosensor. So I see the specificity is also important parameter, sensitivity is also important parameter. So both A and B, this will be the answer of the questions, because if the sensor, if the sensor is a very good, or it has a very useful sensor, then it should have ability specifically detect the parameter as well as a high sensitivity. So if the detector have these two properties, that will be a good level sensor. Okay. Going to the next question. Which of the following is not a technique to immobilize the biorecognition element on the electromagnetically active structures? So which of the following is not a technique? That's a question. You have to see the questions carefully, so there can be confusing facts. So the following is not a technique to immobilize the biorecognition element of the electromagnetically active structure. So using enzymes. So you will have a marker kind of things that should be attached with that your entity to be measured such that you can detect the presence or detect that parameter. So using enzymes, using enzyme is actually good such that enzyme can bind with the different entities depends on the binding properties of the enzyme. Enzyme will bind with the or the substrate will bind with the enzyme on the binding pockets, and if your particular thing is actually similar to that of the recognition of the enzyme binding pocket, actually you can use that particular entity such that will bind with the enzyme using antibodies that bind to antigens. So that is also a specific binding only. So if your entity has a similar kind of structure, which is antigen kind of structure or antibody kind of structure, that will also can be used to bind and immobilize the biorecognition element using aptamer. What is actually aptamer? Aptamer is a short synthetic single-stranded oligonucleotide that specifically bind to various molecular targets such as small molecules, protein, nucleic acid, and even cells and tissues. So this also can be used to bind to the entities which we are going to measure or study. So that three answers are correct using optical fiber. Optical fiber is not like a, it is actually a waveguide. So the properties can be changed, but optical fiber is as itself is not directly immobilizing the molecules. It changes the properties either on the fiber itself or the environment surrounding the fiber, and by that which it can detect the changes in parameter or the parameter of the light and get the get the properties to be measured or get the understanding of, we can understand the properties to be measured by changing the parameter of light which is passed through the optical fiber. But if the optical fibers or the functionalization of the surroundings is not happened, there will not be any direct binding of the biorecognition elements on the optical fiber. Okay. Now you already see in the last lectures there are different properties about the metamaterials are discussed, and we will see a statement. Most significant properties of metamaterials are negative index of the refraction. The significant properties of the metamaterials, they are saying whether it's a due to the negative index of refraction. Metamaterials are actually the engineered things, and one of the main properties of the metamaterial is that it has a negative refractive index itself. So these are engineered structures and which shows the properties beyond the normal materials. That's why the name metamaterial itself came. So what will be the properties of the metamaterial? The main property is that it will show a negative refractive index. Okay. Second statement. The permittivity and permeability of metamaterials are negative as well. What happens in the case of metamaterials? So we already discussed in the class that the different properties like permittivity is positive, permeability is positive. That will be normal material, which will actually act as a transparent material. Permittivity is positive, permeability is negative. It will be like a opaque material, like metals and other things. Then permeability is negative, permittivity is positive, or permittivity is negative, permeability is positive. That will also a opaque material. But when it is coming in this case of a metamaterial, the permittivity and permeability are also negative. So, according to this statement, we can say that a property of the metamaterial is significant because of the refractive index is negative, and the permittivity and permeability of metamaterial is negative as well. The statement one is actually correct, and statement two is also correct, which makes the answer of the question. So, this statement is correct. Statement two is also correct, which makes the option A is the correct answer of the question. Okay. The LC responses of a metamaterial does not depends on the, what is actually the LC response of a metamaterials. So a normal metamaterial things, actually we can actually consider it as a capacitor coupled with a inductor. In that case, what happens? Just see that at an instant, at that particular instant, the capacitor is actually charged. At that particular instant, the capacitor is charged. What happens? So, because of this charge, this is positive and this is negative, there will be a current flow which is flowing through the inductor. But the inductor will not allow the current to flow instantaneously. So, what happens? The capacitor start discharging through the inductor. At the same time, there will be a small magnetic field is created on the inductor. The next time, what happens? The capacitor will get completely discharged, but that whole inductor is completely magnetized. But there will be like a inertial kind of thing which will allow the further current to flow in the opposite direction. What happens? The capacitor will start at getting charged in the opposite direction, and the inductor magnetic field will be decreased, and it will come back to the initial position such that sorry, not the initial position, it will come to a state in which the capacitor is charged in the opposite direction. There is no current flow at all. And this will happens in the alternate manner such that one oscillation is maintained inside the system. If there is a no loss system, Like that way, there is no resistance in the inductor and other things. There will not be any change in the system such that it will oscillate through the system. There will be a oscillation maintained inside the system. Okay. Now let's go to the question. The LC, and this is actually called the LC response. So as normal metamaterial will also deal like a resonated LC circuit. So the LC response of a metamaterial does not depends on width of the splittering resonator. So actually it depends on the width of the splittering resonator. Length of the splittering resonator. So it depends on the length of the splittering resonator also. Properties of the material. Actually, the metamaterial properties actually completely different from the material in which it is made. Metamaterial properties are actually almost we can say it is depends on the refractive index variation from the surroundings and that material, as well as the geometric constraints of the material or the geometric properties of the material. So the width of the splittering resonator matters, length of the splittering resonator matters, surrounding refractive index is actually matters, but the properties of the material is not significant in the case of a metamaterial based splittering resonator. So the answer of your question will be properties of the material. It is not that much matters. Mathematical properties are actually it's a geometric based phenomena. So how you design the arrays actually matters. Okay. Pick the correct statement. Okay. There are four statements are given. We have to see the statements and you have to pick the proper statement out of the four. Please read that. Read the statements. Asymmetric splittering resonators consist of two C-shaped metallic structure which have different center of curvatures but asymmetric arc length. So asymmetric splittering resonator will be something like that way. So it will have two rings kind of structure, but this will have same center of curvature, but arc length will be different. So asymmetric arc length is correct. Different center of curvature is wrong. So this statement is wrong. The plasmon peaks are polarization dependent. The plasmon peaks are actually coming by the reflection itself. So this is not at all a polarization dependent. So this thing also wrong. Snell's law is not reversed in the case of metamaterial, but Doppler effect is reversed. We already know that in the case of a metamaterial, what happens? In the case of a metamaterial, the refractive index is actually negative. So refractive index is negative means Snell's law is reversed. So Snell's law is not reversed is also wrong. Addition of asymmetry in asymmetric splittering resonator leads to a coupled resonance effect between the response of the two resonators. These are actually true. In that case, actually you see that there is actually a coupling is happening between the splittering resonators. In the case of a asymmetric splittering resonators, actually there are two resonance peak you can see. As you can change the asymmetry between the two things, you can see that there is a some coupling happening between the two resonance peaks such that the effect which we can actually modify it based on the change in that asymmetry. So this answer is correct. Okay. A trapped mode is purely reflective mode, purely transmission mode, purely absorptive mode, both A and B. A trapped mode is actually, you can see that in the trapped mode what happens, it's like a the whole, there is no transmission, there is no reflection is happening in that case. It's like a your whole light is actually confined inside that things, so it is looking like a purely absorptive kind of thing. So there is, it's like a completely absorbed kind of thing, there is no transmission and other things at that particular mode. Okay, so your answer will be C. Why are asymmetric splittering resonators are used in biosensing? So because they have a trapped mode. So asymmetric splittering resonators have a trapped mode. That's true. Because they have electromagnetic hotspots and are very susceptible to any change in the local refractive index. So they are purely reflective. They are not purely reflective. None of this. Okay, now you can see that which is the most appropriate answer because they have electromagnetic hotspot. So they have a particular modes at which is actually highly susceptible to the relative refractive index. The local refractive index changes. So if you have some sensing entities there, that may change that particular refractive index in a local manner, and that can actually will change the properties of that modes in that split resonator drastically and can be used as a efficient detector. Okay, so the answer will be because they have an electromagnetic hotspot that are very susceptible to any change in the local refractive index. Okay, now comes the, this is like a direct answer question. What is meant by metasurfaces? So metamaterials are actually materials which is in the form of a, which does not have a refractive index in the form of normal materials. It will have a refractive index which is actually negative in nature. So metamaterial array, which is arranged in the form of a sheet. A 2D structure is called a two-dimensional form of metamaterials, which is called meta surfaces. Okay, so the questions which we have decided discussed here today. Now let us think about the some extra part. We told about optical fibers, total mirror reflection here. Now we will see that how the total mirror reflection can be used in the case of a optical fiber. Okay. Now let us talk about the some extra things about our optical fiber. So we knew that when there is a ray which is actually coming from a denser medium to a rarer medium with the angle of incidence. So this is a denser medium, this is a rarer medium, and the angle of incidence is more than critical angle. What happens? It will completely reflect back to the denser medium itself. So what happens? This can be used to transmit light from one place to another without any loss. So here there is no loss here because the all light is actually reflecting back to its denser medium. And one thing is actually there is no material used to reflect the light. So there will not be any loss because of the interaction with the light and the reflecting material. So we'll see how it can be used to transmit light from one place to another. So this is the principle of optical fiber. What they will have a cylindrical shaped core, which is made up of glass or quartz, and which is surrounded by a rarer medium called cladding. So what happens when a light is actually light rays coming here, then the phase it will bend and it will reach here. At the point, the angle of incidence will be more than that of the refracted angle, sorry, critical angle. It will bend. Go. It will undergo multiple reflection and it will reach the other end of the fiber. And this is actually the basic principle of the optical fiber. There will be a core, there will be a cladding, and there will be like some buffering agent, some chemicals which will protect this core and cladding, and there will be some insulation around this. But the principle is like that way. The light which is coming is entering from denser medium to rarer medium. Means that when it's try to get passed from denser to rarer at a particular angle, which is always maintained in such a way that it will be higher than that of the critical angle. The light is always reflect back to the denser medium. That is like core, and it will undergo multiple reflection and will reach the other end without much loss. This is the principle of the optical fiber. Now, what can be done? The fiber actually we can use it for the sensing. Actually, this can be used for transmitting light from one place to another place, and this can be used to the bundle of optical fiber. Actually, we can call it as a light pipe, and that actually used to and be used in endoscopy to understand what is happening inside our gut and other things. And the same thing, if you are just to use that to visualize, then it will be like endoscopy only. The same thing which can use to give some treatments, because these are light thing, and we can actually pass the laser light through that one, and the laser light can be used to do some treatment at the particular cells where we want. It can destroy some cells, it can burn some cells, something like that. And that's the one thing. Another thing, the the same fiber, the optical fiber can be used as a sensor also. the light can be used as a optical fiber can be used as a sensor, because there are like different sensors and which is sensing area. So there will be like core, there will be cladding, and if we remove some cladding somewhere from here, such that there will be some loss here. But if some medium, the medium inside is actually changing the amount of light, which is the interaction of this core and this medium is actually if the changing the properties of the light which is passes through this one, this can be used as a sensor also. So optical fiber can be used as a sensor as well as and by changing the cladding also, or else with the cladding also, the fiber can be used as a sensor. So if the change the properties of the light which is passes through the fiber cable is changing, then we can use it as a sensor also. So the same optical fiber have a different applications, depends on the usage we can implement. It has a lot of applications in this biomedical areas. Now we can use it as to diagnose. Now we can use it for treatment. We can use it for sensing, and like multiple applications are there for this optical fiber kits. These are the topics actually discovered today. We started with the refraction when told about the different laws of refraction and some what happens when light undergoes from denser to rarer or rarer to denser, and what how it is changes from how it is bending actually. Yeah. Then we came to total and reflection, and the application of total and reflection will be like our optical fiber, and the optical fiber can be used as a sensing agent as well as a to transport. And now it's like, yeah, this whole optical fiber is actually used for communication. What you call it? So like a big communication tool, and that can be used for biosensing also, and like various applications of optical fibers are we can cover. So if you have any doubt regarding this session, please free to ask in the group. If you have any clarifications required, we can ask, and yeah, try to do all your assignments in a proper manner, and we can have a discussion on the assignments which you have already completed also. Let us see what are the requirement you are having. Whatever the your requirement, you just put it in your thing. I'm